Good day. Today you can see that we will start our lecture 33, which defines the design of shafts. Now in this case, you know, the shafts are very common type of members which are used in very widely in any machine designs element, and this is a very important aspects of any engineering systems. If you see, where you can see rotating wheels, etc. Now we go for a formal definition of what we call as a shaft. So we can see we see the definition of shaft as it is a rotating member, and in general what happens that it has got a circular cross section, and this is used for transmission of power. So basically, if you see a shaft, then you must have seen that it is always supported on some sort of bearings like this, some load is there, and there is an rotation, and the rotation of the shaft is caused by some other prime mover which moves or rotates a set of wheels or gears or pulleys like that, and that's the reason we can see that this particular shaft will be always acted upon by mostly, you can see the bending moments and torques and other forces we will see in few minutes. Another important part, just like shaft, we call this component as axle. It is again a non-rotating member used for supporting rotating wheels, etc., and it do not really transmit any torque. It is only acted upon by bending moment mostly. So if you see the earlier day carriages and etc., you can see the axle one is the fixed one, and over which the wheel etc. rotates. And the third one, very commonly known and you have heard of, is called the spindle. It is simply a short shaft, and this word spindle mostly you will be encountering if you talk about a lathe spindle like that. So whether it is a shaft or an axle or a spindle, what you will be finding out that basic design criteria remains almost the same, and it is again based, and it is again, what I mean to say is the application of the basic stress equations what we have learned earlier, and we will also follow the design procedure in the similar manner of combining the different type of stresses that is arising due to different kind of loading that is coming onto a shaft or axle or a spindle. Now here we can see this slide where it is written that standard sizes of shafts. Here you can see that up to 25 mm shaft dial, you can have this as 0.5 mm increments. That means it could be 20.5, 21, 21.5, like so and so forth. Similarly, when it is coming between 25 to 50 mm, normally we have 1 mm increment of the size, and when you go for something around 50 to 100 mm, then obviously the increment step is 2 mm, it will be gradually increasing, and whereas in case of 100 to 200 mm, it will be always it is coming out to be 5 mm increment. Now please remember that this is some sort of guideline of the availability, but there's maybe some changes depending upon the manufacturer, etc. But as far as possible, it is always better to design a shaft based on this type of available sizes, which will obviously make a economic decision. Now, another important aspect for the shaft is its material. Now, when we talk about this material, we are stressing mostly the materials which are somewhat a ferrous type of materials, although it could be non-ferrous too, but here we are giving more attention to the common material which are ferrous types and used widely for any machine components, of course in particular shaft. Now, first one, it is pointed out that the hot rolled plain carbon steel, which comes out to be in the category at the number 1, and as you can see its advantages is least expensive. It is a very utilized material because of its cheapness, but what happens as because it is hot rolled, there is always some amount of scalings that are present, and some sort of machining is always required to make its surface smooth. Next one is cold drawn plain carbon, or it could be also an alloy composition, and as because it is cold drawn, so it has got its inherent characteristics of being a very smooth bright finish, and here you can see the amount of machining is also very minimum, that is obvious, and compared to the earlier one, it has got a better values of tensile strength and yield point. And the last one, which is a very good choice for the cold drawn plain carbon or alloy composition steel, is that its wide acceptability for general purpose transmission. Next one are the alloy steels, which are, you can see it is written that used extensively or relatively extensively for severe service conditions. Whenever the service conditions become severe and means it is demanding also in strength, then alloy steels are commonly used. However, this alloy steel, you understand, is a mixture of many other alloying elements, and so what happens that that all alloying effects has got its own advantages while it is being mixed in the parent steel. So, to retain the total advantage of the alloying materials, one requires a heat treatment of the machine components after it has been manufactured. It has got also some other advantages. As you can see, it has got a lesser tendency to crack whenever you are having a heat treatment, lesser warp and distortion, and these two characteristics are very important when one is going for an heat treatment. And also we can see that the residual stresses are less compared to a carbon steel. But one thing one should expect, that whenever your service conditions are going to severe, you are going to go for alloy steel shafts. Obviously, the cost of the shaft is also increasing to that extent. Now, one of the situation comes that not always the strength of the shaft is very important. In certain cases, what happens that strength is of course a criteria, but it may so happen that the shaft requires to be wear resistant. That means it should have less wear. In that particular case, one has to keep his attention more on to make the shaft surface such that it is wear resistance in comparison. Maybe strength is not that important. So, you know, this wear resistance of the shaft means that one has to harden the surfaces, and the very common type of surface hardening methodologies, that is case hardening and carburizing or cyaniding and nitriding. These are the very common two phenomena what is being normally utilized for hardening the surfaces. And in some of the cases where wear resistance becomes important, one has to go for such kind of situations. Now, once we have some idea of the shaft and its sizes, its materials, then comes the design consideration. So, when we go for the design considerations, you can see that the design of shaft has got two aspects. One is that design based on strength, and the second one comes out in this line is a design based on stiffness. The design based on strength is easily understandable in the situation is that it should able to withstand the external load which is coming and acting onto the shaft. So, we have to take care of the material properties, etc., so that the shaft do not fail. On the other hand, when we consider the design based on stiffness, then it comes to the picture is that even if you are having a strength of the shaft, its deflection should be limited to a desired extension, a desired limit. Means what I mean to say is something like that. Suppose if I try to bend this pen, then what is happening? Well, it is not very much explainable by this particular material because it is quite stiff, but anyway, if you understand that if I try to bend it, then what will happen? There will be a deflection of the pen like this. It may not break altogether, but it will have a simply a large deflection, suppose applied by a relatively a smaller load. This in certain cases is not desirable, or in other words, suppose you apply a torsion with respect to this side. If you apply a torsion, then what happens? This particular material may not break once again, but it can twist to a considerable extent. So, this is also sometimes not desirable. That means, while designing the shaft, then what is the requirement? That neither it should deflect to a large extent, nor it should twist to a large extent by application of external torque. In both the cases, what should be the tolerance level of either the deflection or the twist depends upon the use of the shaft. So, we consider the design based on strength at the beginning, and then we will discuss the design of the shaft based on stiffness. So, for any design, you know, the basic stress equations are always required. And what are these stress equation? It is that again it depends upon the type of loading that is coming onto the shaft. If you remember, or I mean what I mean to say that before going to the basic stress equations, if you just recapitulate at the very first or the second slide, when we talk about a shaft, then what we understand, it is acted upon bending. Suppose onto a bearing support a load is there, then that is a bending. A torsion, that means when it is transmitting on power, and there is a situations where you can also have axial loads that is present onto the bearing, onto the shaft. Now, in this case you can see it is written that a stress arising due to direct shear is normally not taken into consideration. Well, what is this direct stress means? Means basically the shear stress that is arising due to non-uniform bending. I think we have already dealt with this particular aspect somewhere in the beginning lectures for the design for strength. So, in summary, what we can say is that a shaft can have in general the load like bending, torsion and axial load. So, what is happening, that due to the load, bending load, we can have a basic stress equation. Due to the torsion, we can have another equation of shear stress, and again for the axial load we can write down a similar equation of stress which will be normal type. So, if we look into each and every step, then we find that the first one is coming out to be the bending stress. Now, what is this bending stress coming out to be? You can see the expression sigma bending, sigma b denotes as a sigma bending, equals to 32 m by pi d0 cube 1 minus k to the power 4, where m represents a bending moment at the point of interest, d0 outer diameter of the shaft, k ratio of inner to outer diameter, the outer diameters of the shaft. And obviously k becomes equals to 0 for a solid shaft because the inner diameter is 0. Now, let us very quickly revisit that how this particular equation has come. We can see at this size, we know that sigma equals to m y by I. All these equations, or all the notations rather, is very known to you. This is a sigma b. Let me write it sigma b. So, sigma b equals to m y by I. M is a bending moment, y is what? The distance of the fiber of interest from the neutral axis, and I being the moment of inertia about the neutral axis of the cross section. Now, one thing I would like to say, that all these calculations what we are going forth is based on one idea, is that we are considering at this moment the shafts are circular, have the circular cross section, which is indeed the situation in most cases. Now, if you just substitute this value of y, so what happens? The extreme fiber becomes d0 divided by 2, and considering it to be hollow shaft, what is the value of the I for a circular cross section? Pi by 64 d0 to the power 4 minus di to the power 4. So, once you get this one, then you can see that this equation is simply reduced to, from here we can get this sigma b comes out simply, you take out this 64 up, so this is 32 m divided by, if you take pi d0, well, I am writing one short cube because these d0 up and this d0 to the power 4, one power gets cancelled. So, this is d0 cube, and you get 1 minus that di by d0 to the power 4, well, it should be this bracket, say, what we call as this small k. So, you understand that this is the idea from which we find that bending stress comes out to be sigma b equals to 32 m by pi t cube. So, once we see that the axial stress in the similar manner can be found out as we have seen earlier, and this axial stress what we can see is that this is purely sigma axial is this F divided by A, simply F divided by A. Now, we know the area of cross section will be what? This will be coming out to be F divided by pi by 4 d0 square minus di square. So, this 4 goes up, we find it here, you take d0 square outside, which we find it here, and 1 minus k square, because this ratio comes out to be in this fashion. Then you find that a new term alpha has been introduced in this equation. Now, what is this alpha? This alpha you can see is an column action factor. What do you mean? What is the meaning of this particular column action factor? When if you have taken when we have read the first course of the strength of material, we found something phenomena called buckling, which basically is an instability in which cases when a long slender members are acted upon by an axial compressive loads. In the similar situation might happen that if there are considerable amount of axial load or whatever may be, depending upon the length of the shaft, it can exhibit a buckling phenomena, which is normally not to occur if the length of the shaft is not to that large extent. However, this particular column action factor is introduced whenever there is when we compute the axial stress. However, this alpha becomes 1, means there is no alpha, you just erase out this alpha, this equation remains the same as old one we did earlier lecture, when you can have just simply a tensile load. So, when it is coming out to be a tensile load, you can see that alpha value is not taken into picture, means it is 1, basically it is 1. So, if we look to the next equation, whenever the load is compressive, then you can see equations for alpha, which comes out to be of this form. It is 1 minus 1 divided by 1 minus 0.0044 L by K and sigma yc by pi square n by E L by K whole square whenever the L by K value is more than 115, and this is when L by K is less than 115, this is less than 115. Now, this is when it is more than 115, then you can see this particular equation of alpha is something which has got a resemblance with the Euler-Buckling formula, and you can see this n value are having different values depending upon the end conditions. So, n is 1 for hinge type of end, n is 2.25 for fixed ends, n equals to 1.6 for ends partly restrained. As an example, it is given is in bearing. This is mostly highlighted is bearing because most of the shafts do carry the bearings, okay, for the transmissions. So, therefore, whenever you find a bearings at the end strength having an axial load, then of course compressive in nature, then you use a value of n as 1.6, and then if you know the material property, which of course you has to know for designing. So, sigma yield point stress in compression, which comes out to be the value of sigma yc, and thereby you can compute the value of the alpha factor. So, once you put this alpha factor and into this equation, then what you get? You get the value of the axial stress sigma A as 4 alpha A by pi d0 square 1 minus k square. So, we can see that we could find out in last two slides the bending moment expressions of the stresses and the stresses arising due to the axial load. Now, we can see that in the similar manner, when we compute the stress due to torsion, the expression for torsion is tau xy equals to 16t by pi d0 cube 1 minus k to the power 4. Now, this expression comes out to be in the similar manner as we have dealt with earlier for calculating the bending stresses. Here we use the torsion equation. You remember the torsion equation came out to be tau equals to T R by I P. So, it stands like this. This T is the applied torque on the shaft, R is the radius of the surface where you are interested to find out the shear stress, and it will be obviously maximum onto the top surface, and IP is the polar moment of inertia. Again, considering the same way example for hollow shaft, we can see that this comes out to be equals to T d0 by 2 and IP will be pi d0 to the power 4 minus di to the power 4 divided by 32. So, this 32 goes up, divide by 6, so that comes out to be 16. T is present as usual, pi is here, you take out d0 to the power 4, then 1 d0 is above, so it comes out to be d0 cube, and as you have taken out d0 to the power 4, this comes out to be k to the power 4, where you know the k is a ratio of di to the power di by d0. So, eventually if the k is 0, means for solid shaft you get 16 T by pi T 0 cube. Now, here you can see that subscript xy has been given in this tau xy, but here I have not used. It is a general expression, but here if we just I will just talk about this xy when we take a typical element onto the shaft surface. Okay. Well, let us put xy to have a same identity as this one. Now, we come down to the next slide, which shows the combined bending and axial stress. So, we know that from the compound stress ideas that the normal stresses, that is sigma bending which is coming out to be here, and this particular one which is the axial stress, both are of the normal stress nature, and we can combine it together and it gives a idea like this, and the total sigma x comes out to be plus minus. Now, here is one situation that I have given a plus minus at the beginning, and so that is the reason this is the maximum normal stress summation of the bending stress and this one. So, just let us have a quick idea of how we are making the summation. Now, you see that we can have a shaft, okay, and this is the center line of the shaft, and suppose it is acted upon by a torque T. So, it will be acted upon by a torque T, and due to some loading somewhere onto the shaft, suppose at this particular section AA some amount of bending moment is coming into picture, whose magnitude is m, and it is this particular bending moment, suppose it is in this manner. You understand what I have drawn? Means a typical bending moment coming and being acted in this particular manner. Okay, so the figure you can see, and this bending moment which is appearing at the section of interest must have come from some reactions at the bearings and the external loads onto the shaft, that we understand. So, once it is coming into picture, then what will happen, that we can analyze this particular section over here, then we can just think of the free body diagram. Okay. So, at this moment we can see this is the exposed one, and we can think an element somewhere at the top of the surface. You understand, this is the element top of the surface. So, if we look at the element and look at this torque, onto this face, what will be happening? The torque will create a shear stress like this, and we consider this axis of the shaft to be x, and obviously in two dimensional this will be something like y, so that we can denote this shear stress as tau acting onto the x plane in the direction of y. So, this is one, and if we look this view, then we have drawn this as tau x. So, you can immediately find out the other stresses. Now, as we can see that we have made a bending moment in this way, means we have been bending in this fashion, M is coming. So, upper surfaces will be compression, lower bottom side will be tension. So, if the load, axial load is in tensile in nature, this is tensile load, then what is happening? That you will be having maximum sigma x in the direction of x, that is a sigma x will be sum of descending due to bending stress plus and this tensile stress plus sigma x. Okay. If on the other hand, if we find that the load over here is compressive, then the sigma x will be maximum here in the top surface, and that is coming out to be what? This will be coming out to be equals to that minus. So, that is the reason the maximum sigma x which can come will be always written as that sigma b by sigma a. Well, depending upon the situation, one is tensile and you are interested, that will never happen, because you will be always looking for the what? The most stressed point. In the same manner, if you just recollect that we have been talking about in the slide, one of the few slides early, that normally we do not take the stress arising due to the direct shear. What is the reason? See, if you can consider the direct effect of the direct shear stress, and you must remember, you must have this read earlier, that means the shear stress variation comes out to be something like that parabolic, which becomes maximum at the center point and value zeros. Here it becomes 0, 0 stress, and this becomes your maximum at the center point. So, what is the value here? This is direct, this is 0. Now, in the similar manner, one can say, if I take over here, then we get the direct stress to be maximum here. But if I take an element at this point, you can see sigma bending must be 0. So, normally what is being happening, that onto the shaft, the effect of the bending stress comes out to be relatively quite large. Okay. So, that is the reason it is a standard idea that you consider sigma bending, you consider sigma axial, and you consider shear stress tau, which comes due to the torsion. So, here by this figure we can see that how the summation of stresses are being taken into account. So, we go back to our earlier slides. So, we can see this is the ideas for the maximum normal stress. Now, we go back to one of the very classical theories of failure, that is called that maximum shear stress theory. What is the maximum shear stress theory? If you recapitulate, we have learned earlier, which states that a machine member fails whenever the maximum shear stress at a point crosses the maximum allowable shear stress for the material. That means, material strength in shear should not be lower than the maximum shear stress arising due to external load at that particular point, which in short defines the tau max is the maximum shear stress, that is coming as tau max, and this tau max is equals to tau allowable or the working, and that is given by as a square root of sigma x by 2 whole square plus tau x y whole square. So, now you understand this sigma x notation and this tau x y notation, and accordingly we can write down this expression, and